So for a full wave bridge rectifier, which we see right here, we actually have 120 volts RMS coming in, and we have at 60 hertz. So one thing about a full wave bridge rectifier, and we'll talk a little bit about this inside, is that you're using the full voltage of your RMS on your secondary, right, which is great. So we're going to call this RL. Just give that an RL right there. So first of all, the secondary voltage, well, we saw that in the last video on how to actually come up with the RMS value. Remember, if you measure this on a DMM, digital multimeter, you're going to get an RMS, and that's root square voltage. In this case, we have 120 volts, a 6-to-1 ratio, six turns in the primary to 1 turn in the secondary. That's what that means. Iron core transformer, and then full bridge has 4 diodes. So on a test, I'll be asking how many diodes does a full bridge have. In this case, it is 4 diodes, and each diode runs about 0.7 volts. Remember, I'm just using that 0.7 as a rough estimation. If you were going to get a true value of this, what you would do is you would take and you would measure across this using a multimeter, digital multimeter that has a diode check on it, and you could come up with the exact value. I recommend that if you're actually doing, if you're working in anything that requires precision. So secondary voltage RMS is 120 volts, and we're going to say that's an RMS. And this is the number of turns we have in the primary. So that gives 120 volts, 20 volts RMS. Our voltage peak is 20 volts RMS times by 1.414 gives us 28.28 volts peak. Now, the volt out peak, which we're looking at, is right here. So this is V out peak right there. The out peak is you're taking your voltage peak and you're going to subtract it off by 2 times the diode. So each diode is 0.7 volts. We get 2 times 0.7, which gives us 1.4. Remember, our diode acts like a small little battery there. So with this in place right now, we can actually do and come up with some other values here. We can come up with a ripple, and we can come up with voltage DC. So I'm going to do is voltage DC without ripple is going to look like this. This is DC average, AVG, is going to be equal to 0.636 times that by your V out peak, V out, and then there's the P right there. So what we have right here is we take our calculators and we take 0.636 and we multiply V out peak is, sorry, I didn't finish that up, 28.28 minus 1.4 gives me 26.88 volts out peak. So 26.88 volts out peak. So 0.636 times that by 26.88 gives me 17.09 volts DC. So that means we should have 17.09. So a lot of people have been asking, okay, where does this 0.636 come into effect? Well, if we take and we look at a half-wave rectifier, we know that if we take 1 over pi, we get 0.318. So 0.138 actually represents a half-wave rectification signal. This is a full-wave rectification signal, so we need to get 2 times this. That's where we get the 0.636 from. It's 2 times that 0.318 because we're using full wave on that. A couple other things on here too we want to look at, and we'll talk about rippling in a second, is our frequency. Frequency is equal to 2 times our input frequency, so 60 hertz gives us 120 hertz, which comes out to be 1 divided into 120, which is reciprocal of it, gives us 8.33 milliseconds. Pretty good stuff so far. I think we're doing pretty well with this. So with all this information, we can actually find our ripple voltage. And let's see if I could get this thing a little bit better on here for ripple. I don't think so. I'm going to have to erase some stuff here. Let me see what happens. Let's see. Can I get that? Yeah, I can. So V ripple is equal to, and I'm going to put it on the bottom. This is going to be your V out peak. So V out peak times 1 minus E negative T divided to RC. So we know that the negative T is going to be equal to the 8.33 milliseconds. And our R is going to be our load, our L, which is, let's say this is 100 ohms. I'm just going to put 100 ohms right here. And the capacitor, C, well, capacitor, it goes in parallel with here. So if I put a capacitor in here, and I say that's C1, and I say C1 is going to be equal to 4,500 microfarads. So if we put that whole thing, that whole part into the equation, we get a value. So if we take and we plug all these numbers into this equation, our ripple actually becomes 0.493 volts ripple. We'll talk about what ripple looks like in a second. So that's not much of a ripple. To be honest with you, that's a half a volt of ripple, and that's a little bit, but it's not too bad. We can actually get it down further. And remember, if you put capacitors in parallel, your capacitance increases because that's your plate size is increasing. And so if we put two capacitors, we can see that if we take two 4500s, we put it into here, into this circuit here, what we can actually get is this 0.493 almost goes right down in half again. So you're talking goes down to 0.25 or 250 mils of voltage, which is pretty good. Last part of this is V out DC. This is our DC voltage. V out DC is going to be 26.63 volts DC. Now, for those who are in engineering, whoever looks at this, they're probably thinking, well, these are rough estimations. And I'm like, yes, it is. This is good for those who are looking to become a technician, looking to become, they're trying to maybe go into pre-engineering to get an idea of what's going on. But this gives you a rough estimation. It gives you a real good rough estimation of everything that goes on. So if you have any questions on this, please feel free to contact me, and I will answer your questions. Thank you.